Hi everyone, I'm Supritha. Welcome to week 10 live session for the course Dynamics for Astrophysics. We'll first revise the material that was covered in this lecture and then we'll solve some sample problems. All right. To remind you, we were discussing MHD and currents in MHD. Things like currents have no sources or sinks and so on. And where does this come from? So if you remember, this was the relation one got when one did frame transformation from the fluid frame to lab frame, and E and B are the electric and magnetic fields in the lab frame. Um, when observed from the lab frame, E and B are the electric and magnetic fields in the fluid. V is the velocity of the fluid, uh, and when one uses this relation in one of the Maxwell's equation, you get this relation. You trade del del t for V cross B, and you get this relation. And if the fluid is non-relativistic, then you can ignore this term because this comes with a factor of V by C square. And then what you have is curl of B is equals to 4 pi by C J. And this was discussed last time, but good to revise. If you take divergence on both sides, this term drops out because divergence of curl is 0, and you get divergence of J equals to 0. What this tells you is that the current has no source or sink for non-relativistic fluid. Okay, and we also looked at the continuity equation where del rho del t was related to divergence of J, and since divergence of J is 0, del rho del t is 0, which means that the starting assumption in MSD, which was that the plasma we are working with is neutral. We are working at scales where the plasma is neutral, and we can't make out the different charged particles from each other. We are working on much larger scales than that does not allow us to make out the distance, the different charged particles. So we're working on scales where the plasma is neutral. And if we start with that assumption, the plasma remains neutral as the fluid evolves, and along with it the magnetic field. Okay, as the magnetic field responds to the flow of the fluid. All right. uh, Also, this current that you see, this is not due to charged particles in plasma. This was emphasized in the lectures that this ray is not due to charged particles in plasma. This is uh, simply because of curl of B. Okay, this is the analog of displacement current. This is not because of actual motion of charged particles, because remember, in MHD, we are dealing with a picture where we don't really have charged particles. We're working on a lens case where we are working with the continuum approximation, with the fluid approximation. Okay, so we're not really dealing with charged particles. This current is not due to charged particles. This is simply a proxy for the magnetic field curve. Okay, and once again, it is true that the fluid which is immersed in this magnetic field, this fluid does carry a current, but this current is not because of motion of charged particles in the fluid. It is simply because it is immersed in the fluid is immersed in a magnetic field, and the magnetic field has some non-zero curl. It's this non-zero curl of the magnetic field which is responsible for the fluid carrying this current J. It exists because of curl of B. Okay. Sure, the flow profile, this V, certainly determines J. Because you see that if you look at the induction equation, you will see that the evolution of the magnetic field depends on this V. And if the evolution of the magnetic field and hence the evolution of the curl of V determines J, sure, its evolution depends on the flow, but it doesn't exist because of charged particles in the flow. It exists because of some curl of V. Okay, this is entirely some displacement current analog from your electrodynamics. This is not your usual conduction current. Okay, all right. Now, if you want to write down the equation of motion, the momentum conservation equation for such fluids which are immersed in magnetic fields, we have to look at the extra force that arises because of the fact that there are magnetic fields. And what is the extra force? There's some Lorentz force. Simply because the fluid has there's some current flowing through the fluid. Okay, what's the Lorentz force is given by J cross B divided by C. And we just said that for non-relativistic fluids, we know what the current is. So we substitute that over here and we get that the Lorentz force is simply curl of B cross B divided by 4 pi. Okay. Now we can add this to the momentum conservation equation along with other relevant forces, let's say the body force or the gas pressure force, and solve. Okay. So what are the variables that we'll be solving for in this situation? The two main variables that we are solving for is V and B. The flow of the fluid, the velocity profile of the fluid, and the magnetic field. Okay. And we have two equations for that. What are the two equations? Induction equation and momentum conservation equation. These are coupled. So you can solve for these two variables, and you will get J as a derived quantity, which depends just simply on curl of P. Okay. And this was also discussed that in MST, usually you model the flow profile, you know the flow profile, you guess the flow profile, and you solve for B in astrophysical context. All right. Okay. Now look at this momentum conservation equation. Recall that this was the divergence of pressure tensor, where the pressure tensor had a scalar part and off diagonal parts, the anisotropic stress tensor. Hmm? Now what we can do is we can compare this term and this term, and we can say that well, they are on the equal footing, so it should be possible for us to rewrite this term as divergence of a tensor again. Okay, so what do? We write this, and it can be verified that this M is actually a tensor given by this expression. The derivation is not very important. The point is you can take some B. Let's say you can try for B0 I cap or some other B, and you can test that this and this are the same. Rather, this and the divergence of this, they are the same. Okay. So once you've convinced yourself that this is indeed true, we recognize this term as the scalar stress and this term as the tangential magnetic stress. This is the diagonal part of the magnetic pressure tensor. These are the off diagonal parts of the magnetic pressure tensor. We place this gas pressure term and the magnetic pressure term on equal footing. All right. Okay. Now, what we can do is look at this term. Look at this term. Now, remember that the way we derived this momentum conservation equation was on the left hand side, we wrote the term which is equivalent to dp dt, and on the right hand side, we wrote down all the forces. And then we integrated over some volume element. Uh, so, can you still see my screen, by the way?
Yes, it's visible. Right?
Can you see what I'm scribbling on it?
No.
No, right? Turns out I have left the meeting. Okay, let me see. Yeah. Just give me a minute. I'm so sorry for this. There's some glitch. Um, just give me a moment. My Wi-Fi got disconnected from my iPad. Hold on, huh? Just one second. All right. Let me share my screen again. Okay, good. All right. So remember how we derived momentum conservation equation? We wrote down an equation which was dp dt equals all of the forces, right? And then we integrated over some volume, and then we said that since this is over any arbitrary volume, arbitrary non-zero volume, whatever is the integrand must be equated on both sides, That is how we got this. So what we do is let's integrate this term over some volume. This using divergence theorem, this gives us m dot dA, where dA is along is the vector along the orthogonal to the surface, right? Which we denote by n cap. Okay, and we call this term as the Lorentz force per unit volume, right? So we know what Mij is. We just wrote down this expression for Mij. We figure out that the first term, where delta Ij multiplies n cap, is just going to give you a b square n cap, right? And the second term, where one of the bi's multiplies n cap, is going to give you a b dot n cap, which was written as bn in the lectures, times b vector. Hmm? And this comes with a minus sign. All right. Now, uh, take a certain fluid, uh, take a certain volume of the fluid. Hmm? Uh, let's say you have B fields along Z axis. The surface area is outward along this direction. Hmm? Uh, now from this, what can we say about how the magnetic field lines will respond to deformations? Okay. Now, you see that the Lorentz force has it has two components. One component is along n cap, which is along the direction of the vector uh, perpendicular to the surface, and another one is anti-parallel to B vector. So it's in this direction. Hmm? And what you can also do is you can argue that I'll balance these components against minus grad P to get the direction of the components. Now, if you remember, in this equation, we got a minus sign in front of grad P. Why? Because pressure is traditionally, the notation we use, the convention we use, is that pressure will act inwards on the fluid element, right? That's why this minus sign compensates for that. Hmm? So this entire term tells you that you have a force acting inwards on the fluid element, right? And on the right hand side, what you have is minus FL because of this minus sign. We called FL as n dot m cap, right? So under steady state, under no acceleration of the fluid element, what would balance what? The gas pressure term would balance this Lorentz force term, right? So we see that an inward pressure acting along this direction would be balanced by what? This n cap. But this n cap comes with a positive sign because you've taken it to the right hand side, right? So this n cap will be outward. So this term is actually a force which pushes you outwards. Balancing what? Balancing an inward pressure. Okay. And let's say you have this once again, this thing. Let's say you consider a surface over here. The pressure would be acting in this direction. But FL on the right hand side that balances this pressure comes with a minus sign, right? So what happens? This minus sign will be along this direction. Okay. What this tells you is if the magnetic flux increases in this fluid element, in this volume, if the magnetic flux increases, if B increases, right, FL increases, and to stabilize that, what is the net force if B increases? It's along this direction, along n cap, outwards, hmm? And along minus B, where B is along the Z direction, so minus B would be along minus Z direction. Okay. So what does this tell you? That it's resistant to deformation. If you squeeze it, if you try to squeeze the volume element, if you try to squeeze the magnetic field lines together, if you try to increase the magnetic flux, what will happen is it will pull you out. It's resistant to deformation. Okay, all right. And this is even more relevant when you have this. You'll see the effects are more pronounced when you have curved flows, let's say, and when the fluid, when the magnetic field lines are being concentrated together, let's say. Okay, that's why you see the effects of magnetic stress tensor, magnetic pressure. All right. Uh, Next, what was discussed was the concept of magnetic buoyancy. All right. So, where does this come from? Look at the momentum conservation equation. On the right hand side, we had a gas pressure term and a magnetic pressure term, which we combine together to write it as MT. And the right hand side we simply write as divergence of MT. Okay. Now let's look at a fluid flow, right? This is the same fluid in both these regions, but one of the regions has some pressure P1, magnetic field B1. The other region has some pressure P2, magnetic field B2. Okay. The black line is what separates these two regions. All right. Let us say that the magnetic field in the region 1 is more concentrated than the magnetic field in 2. All right. Now, what can we say about the gas pressures? If we know that the magnetic pressure is, let's say, the magnetic flux is more concentrated in one of the regions, this is what we can say. Consider a very small volume element over here with a vanishingly small thickness, and consider the right hand side. Let us integrate this over this volume dV. If epsilon is vanishingly small, what happens to dV? It becomes vanishingly small. This integral goes to 0. Let us use this to write this as m n cap dot mt dot n cap. Okay. Now mt we know is this. It consists of the scalar pressure. Here we have assumed that the fluid is not viscous, so there is no off diagonal elements for the pressure tensor. Mt consists of the scalar pressure. It consists of the scalar part of the magnetic pressure tensor and the off diagonal part. Okay. Now the off diagonal part we just saw acts perpendicular to n cap, right? If you're considering a very small fluid element, even if this line is curved, this can be approximated to be this. And we just saw that this term, the direction of this is perpendicular to n cap, which is being dotted over here with mt. So what is it? It's actually 0. That's why Bij is ignored. Okay. All right. So what are we left with? We're left with this p plus b squared by 8 pi is equals to Buck constant, because we are integrating this, right, over this surface. So we'll have to equate this quantity on this side equals to this side, which gives us this equation. What does this tell you? This tells you that if the magnetic field is larger on one side, if you have a region of high magnetic field, that will be the region of low pressure. And low pressure, if you have the same temperature, means low density. Why? Because P is stroke Okay. And regions of low density equates, you observe buoyancy over there. All right. Okay. A few more things. Plasma beta. So you realize that we have defined various dimensionless quantities along the way in this course. One of such dimensionless quantity is plasma beta, which is defined as the gas pressure divided by the magnetic pressure. The gas pressure divided by the magnetic pressure. Okay. Now, uh, uh, one point to note is that beta being smaller than 1 or larger than 1, which means that gas pressure being smaller than the magnetic pressure or larger than the magnetic pressure, does not tell you that you can drop uh, the gradient of P term in the equation of motion or the Lorentz force term in the equation of motion, because these are pressures, whereas the force terms that come as a result of, let's say, the gas pressure or magnetic pressure, gradient in the gas pressure and magnetic pressure, they have other they depend on, let's say, the gradient or curl of P, right? So this ratio tells you nothing about which contribution is more important as opposed to the other, and you can't simply drop, let's say, the Lorentz force term if beta is much larger than 1. Hmm? Beta larger than 1 just means that the gas pressure dominates over the magnetic pressure. All right. Uh, Also, terminology. Uh, you can be told about force tree. You can be given a, let's say, in questions you can be asked, what's a force tree configuration, or let's say you're given a force tree configuration, what statements hold true. So force tree configurations are just those on which Lorentz force is 0. When can a Lorentz force be 0? When J cross B is 0, right? And J, if you remember, was curl of B. So if curl of B is parallel to B, then J cross B is 0. And in such configurations, if you have such fluid flows immersed in such configurations of magnetic fields such that the curl of B is parallel to B, if you can come up with such magnetic fields, then the Lorentz force on such fluids is 0. These are force-free flows, let's say, force-free configurations of magnetic field. Okay. All right. Now comes a very important discussion, which is flux freezing. This happens for perfectly conducting fluid, because you will see that to prove this, we will ultimately use the magnetic induction equation, which holds true only for perfectly infinitely for fluids whose conductivity is infinite. Uh, we'll prove this, but we'll review the proof. What does this tell you? This tells you that the magnetic flux is conserved. So let's say you have a fluid flowing and you have magnetic flux passing through the flux lines passing through the fluid, right? Uh, this tells you that phi is conserved. And if phi is conserved, if phi has to be conserved, then let's say you consider a flow like this, right? Where these are, let's say, the boundary of your fluid flow, and you have magnetic field lines along the fluid, along the flow. Hmm? Now, if this flow tapers, then your magnetic field has to become more concentrated. So the flux lines, magnetic flux lines, will respond to flows as if they're frozen into the streamline, as if they're frozen into the fluid. So if the flow forces the fluid to taper off, if the flow forces, if the pipe, let's say, carrying the fluid tapers off, of course, there are no pipes in astrophysical settings. I'm just telling you that if the flow tapers off, then the magnetic field will respond accordingly, because it's as if it's frozen into the fluid, and the flux will increase in this region where it tapers off. Okay. And we'll see why this is true. All right. So once again, let's consider this diagram. All right. Uh, so clearly this is wider in this end and thinner in this end. Let's say the fluid that has passed through this region has passed through with a velocity of, let's say, vt at time t, and it has reached this position at time t plus delta t. So this entire thickness is v times delta t. Let's say v remains unchanged. Okay, v times delta t. All right. I will be denoting by capital S surface area, which is uh, along the cross section. So let's say this surface area and this surface area will be denoted by capital S at t and at t plus delta t. And the small s will denote a line element along this loop. The small s will denote a length segment along this loop, these two loops. Okay. What is sigma? Sigma is the area which is basically this. I hope the notations are clear. Okay. Now we can clearly see that the flow cross section is changing clearly. So what is happening to the flux? How will the flux respond? Okay, so let's see. How will the flux respond? We'll have to, for that we have to compute the change in flux, right? So what is the change in flux? The change in flux along the flow, remember along the flow is whatever quantity exits this, and we are considering B outwards as positive and B into the volume as negative, right? So what is the change in flux? The change in flux is whatever flux goes out, which is B dot ds, but this B will be at T plus delta T, and this S will be S at T plus delta T, minus whatever flux goes in, through this. So remember the B fields are like this. So what has gone out is given by this, and what has gone in will be given by B at T times the surface at T. ST is this. Okay? Alright. Now we can add and subtract a term which is B at T plus delta T times ds, where S is the surface area at T. Okay? When we do that, this term combined with the first term, let's call that I1, and this term combined with the second term, let's call that I2. Let's look at the structure of I1. I1 is the same magnetic field multiplied to the difference in the surface area at T plus delta T and T. What does that tell you? That if the magnetic field were to remain unchanged, then this term gives you the contribution due to the change in the loop position. You are changing this loop from here to here, you're going from this loop from here to here, and you get a change in flux. What is the change in flux? It's given by I1 because we're holding B constant. Okay, so this is purely due to this. This is the change in flux purely due to the change in the loop position. Okay, and look at I2. For I2, we're holding ds fixed. We're holding the loop fixed at T. But what we're doing is we're subtracting B at T plus delta T from BT. Okay, so what does this give you? This tells you that you're holding the loop position fixed. You're just considering this loop, but now you're considering contribution to change in flux coming just from the change in magnetic field. Of course, there are changes in B as well as changes in the loop, changes in B as well as changes in the flow, right? That is what both of these contribute to the change in flux. Flux is B dot ds. There will be change in the magnetic field as well as change in the surface area in the cross section through which the flow goes. Right? There are changes in both. What we have done is we have managed to separate these two contributions into I1 and I2. Okay? Okay. Now, since I2 is a change due to change in B, change in flux due to change in magnetic field, what does that mean? That means it's simply this term, right? Of course, if you take this inside, this will give you dB dot ds, which is the change in B. Okay? Alright. Now, consider the divergence of B is equals to 0 at a particular time t plus delta t, and then integrate over some volume V. So divergence of B was 0. We integrate this over some volume V. Over what volume V? Over this volume. Okay. And of course, divergence of B holds at every point in time. We are just considering it at t plus delta t. Right? So let's look at the different terms that will arise. What is the divergence of B? It's the flux of B into this volume, right? So what are the different directions from which this flux the B field lines can pass through this volume? One is this clearly. Another surface area is sigma, right? So what do? We write the term that gives us flux from this surface at t plus delta t. We write this term that gives us the flux from this surface And remember, all of this is happening at t plus delta t, so we'll consider B at t plus delta t. Because we know the divergence of B equals 0 holds at every point in time. We are just looking at this equation at t plus delta t, right? So, and we are just labeling we are labeling this surface by S at t plus delta t. If it confuses you, you can call this S2 and S1. Okay, it's not that this surface pops up at some future time. We are just labeling the surface as t plus delta t. Okay, so what contributions will this have? One contribution is B at t plus delta t passing through the surface minus, because this contribution will be into the volume, minus B at t plus delta t times the surface at t plus whatever flux line crosses via sigma and enter the volume. Okay, so this thing. So this term is the flowing out thing, this term is the flowing out thing, this term is the flowing in thing. Okay, now look at this term. What is this? Suppressing this label t plus delta t. What is this? This is p dot v sigma, right? Now d sigma is what? It's some ds cross v dot delta t, where ds is a line element along this loop. So the surface area, which is the surface area of, let's say, cylinder, is this line element times this line element. This gives you the surface area of sigma, which is ds times this length being v delta t. So we write this, and this cross product gives you the vector which is pointing outward from the surface. That's why this cross product. Okay. So what does this give you? That gives you a b dot ds cross v. But we know that a dot b cross c is b dot c cross a. So we use that over here. We just rearrange this a dot b cross c product, this triple product, and that gives you this. But this remember, this ds is a closed loop, and this is in the exact form of curl theorem. So we can write this thing as curl of b cross b times del t dot ds, where this s is capital and this is now the surface area, this surface. Okay. What was all of this? All of this headache was for b dot sigma. What was b dot sigma? This was this element. And how does it relate to these two terms? Well, this term is just the minus of this. And what is this? If you focus, you will see that this is just I1. You see that I1 was B at t plus delta t multiplied to the difference in the surface area at t plus delta t and t. Difference in these two surface areas multiplied to B at t plus delta t. This is exactly what this is. So this is I1, which is minus of this term, because this entire thing is 0. And what is this term? This term is this. So we write I1 as minus of this. Okay. So what do we have? We have I1 and we have I2. And now we add these two. Why do we add this two? Because remember, we were focusing on calculating the change in flux due to the change in flow, cross section, and magnetic field at these 2 points, right? And del phi was I1 plus I2. And we see that I1, I2 are these two things. So we add them and we see we get such a thing. Now what do? We use the induction equation for infinitely conducting fluid, which tells you that this is 0. And if this is 0, that means del phi is 0. What does that mean? That means that a change in the flow cross section does not, it just implies that the flux will not change. Okay. So if you have magnetic field immersed in this fluid, it will evolve, respond to flow changes as if it's frozen into the fluid, right? It will move with the flow as if it's frozen into the flow. Okay. All right. Now, once you try to apply these things to astrophysical context, you will require a model. You'll require an explanation for, uh, let's say you observe some fluid in some astrophysical context, right? And then you want to explain how the magnetic field lines, why the magnetic field lines evolve, how they evolve, given what you know about MHD, right? What are the things that such a theory, which is called a kinematic dynamo theory, should tell you? It should tell you, well, how did the magnetic fields grow to that strength in the first place? Because in astrophysical settings, magnetic fields can get quite strong, right? How did they grow to such scales? And what is sustaining them against decay? Because remember, all of this is for an infinitely conducting fluid. In real situations, you will have some finite non-zero resistivity. The conductivity might be high, but it won't be infinite. In such situations, the magnetic field will decay slowly but eventually. So, what is, and the calculated time scales, let's say it was told in the lecture what are the time scales of uh, the decay of magnetic field in, let's say, the sun or the earth. But we do observe magnetic fields, and the sun has lived for much longer than those decay time scales. So, uh, what is reviving those magnetic fields in this medium? What is making these magnetic fields persist in spite of resistive decay? Any such theory should be able to explain these things. Okay. One of the examples of such a dynamo theory was given in the lectures, which is a solar dynamo. To explain to you some certain things like what is the solar cycle? The solar cycle is where the polarity of the magnetic fields flips. This happens every 22 years. One of the popularly believed model that works is this omega alpha model that was discussed in the lectures. I will review this. We'll just revise what are the features of this model. Okay. Uh, all right. So one of the key features to explain this flipping is to note that our sun has differential rotation, which means that the rotation period at the equator and the poles are different.
Ma'am, I had one question regarding this polarity changing. As far as I knew, like the solar cycle is for 11 years, no, ma'am? The polarity changing means it's happening separately for the northern and the southern hemisphere.
The
That's why it's
polarity
20.
change. Can you come again? Can you repeat?
Actually, ma'am, what I knew was like for the solar cycle, it happens for every 11 years. So,
The
uh,
solar maxima to minima happens every 11 years, I think.
okay, ma'am, like it's
So a
happening
full
separately.
cycle.
Yes, ma'am, continue.
So I'll show you diagrams. So the solar maxima to minima, that is when the fields become from poloidal to, let's say, toroidal, and I'll tell you what poloidal and toroidal mean, right? Um, that happens every 11 years. So that's the change from solar maxima to minima. And to go back to the solar maxima, where you will now see that the poloidal fields are now flipped, the direction is now ulta. You will see that happens every 22 years. I'll show you diagrams for that.
Okay, ma'am.
Okay, okay. All right. So let's go step by step. So one of the key features, one of the main uh, ingredients in explaining this thing is the differential rotation of the sun. Okay, what does this mean? This means that the rotation periods at the equator and at the poles are different for the sun. At the equator, it's about 24 days. At the poles, is about 38 days. Right. So what does that mean? Since the sun is not a solid object, clearly it's a ball of, let's say, plasma. It is allowed to have different rotation periods at different altitudes. What are altitudes? Altitudes are basically these angles. So at different altitudes, it's allowed to have different rotation velocities, right? It's fastest at the equator. It takes just 24 days to go around. Slowest at the poles. Okay. These numbers you can cross check. This was taken from Wikipedia, I think. So once you note this, then comes the omega effect from this omega. The omega effect. What is the omega effect? That a magnetic field, which is, let's say, directed from, let's say, north to south, I should probably, from, let's say, north to south, right? What is this magnetic field observing? It's observing, and remember, it's passing through the plasma. It's passing through the fluid. It's immersed in the fluid in the plasma of the sun, right? And what does the plasma of the sun do? It has some differential rotation velocity, right? So it rotates here the fastest and here the slowest. But this magnetic field is frozen into the fluid. So how will it respond? It will respond by deforming. It will respond by deforming, right? So what happens is such a magnetic field, which is poloidal in direction, will start getting some azimuthal component. It will start wrapping around the sun, right? And it will start becoming toroidal slowly. Why? Because it gets dragged along with the differential rotation, with the fluid which has some differential rotation. That's why. Flux freezing is very important over here. Okay. And when that happens, this is the omega effect. This is the poloidal magnetic field getting some azimuthal component wrapping around the sun, becoming toroidal. Okay. All right. Then comes the alpha effect.
Actually, is it called omega because of the shape of
Yeah,
the deformation?
probably. Yeah, probably. No, but I think it's called omega because of the rotation, because it's primarily because of the differential rotation of the sun,
Okay.
I guess. Yeah. Okay. All right. Now to explain the alpha effect, I think it's better to go to diagram than words, and then we can come back and review what is written over here. So let's look at this picture. Due courtesy to this astronomer. Okay. So what is happening is, let us begin with the sun and poloidal field lines like this. Okay. Due to differential rotation, the fluid will drag the magnetic field along it, and this will cause in the magnetic field lines becoming slightly toroidal. It will get some azimuthal component, right? Eventually, what will happen is all of it will wrap around the sun, and the magnetic field becomes toroidal. These are called poloidal magnetic fields. Poloidal configuration. This is the toroidal configuration. Okay, this is the omega effect. Now, how do we go from here back to here? In a span of 22 years, how do we go from here back to here? Okay, all right. Uh, See, what happens is, there are, due to reasons, and of course this alpha effect is not, the people are still studying it. There's no clear answer as to uh, uh, what exactly is responsible for this. But the most popular understanding is, let's say, for some reason, we'll skip the details. For some reason, let's say plasma is radially convected outwards from the interior of the sun, right? So what is happening is, from the interior of the sun, plasma is convected out. Okay. Now, as it is convected out, as it is traveling out, what will the plasma see? It will suffer Coriolis force, right? Because it's in a rotating frame, so it will see that it's getting deflected because of Coriolis force. Okay. What is the direction of Coriolis force? It's omega cross u, where u is the velocity of this plasma parcel, and omega is the angular velocity of the sun. Okay. Note that for an observer in the northern hemisphere, the direction of omega is upwards, and for an observer in the southern hemisphere, this direction of omega gets reversed, because then the observer will see omega inwards towards the ground. Okay, so omega gets reversed for two observers in the two hemispheres. Okay, omega gets flipped. All right. Okay. So what happens? Because it's experiencing a Coriolis force, because this plasma parcel is experiencing a Coriolis force as it is traveling outwards, as it is being convected outwards, as it's traveling from the interior of the sun, what is happening is it is experiencing some twisting. And we know that magnetic lines follow the fluid flow. So what will happen if the fluid twists due to this Coriolis force? The magnetic field, these magnetic field lines will also twist. How will they twist? They'll twist like this. Now, if I ask you about the direction of the twist, if I ask you about the direction of the Coriolis force, you will see that this twist, the direction of this twist is the same in both these hemispheres. Why is that true? Because two things get flipped, which compensates for so two things compensate for each other, and that gives you the same direction and twist. What are the two things? The fact that the field lines are opposite to each other, they're flipped in the northern and southern hemisphere when the sun is in the toroidal configuration of magnetic field, right? In the northern hemisphere it's along this, in the southern hemisphere it's along this, and the Coriolis force is also flipped in the two hemispheres. Why? Because omega is, because observer sees a different flipped omega, right? So what happens is when you combine these two things, you will see that the twist, the ultimate twist in the magnetic field is along the same direction. Okay? Okay, sorry, it's along this direction. All right. What happens? What happens then is this is happening throughout the surface of this sun. It's happening throughout, right? So this is the tricky part that we won't go into the details about. Magnetic diffusion will cause these small loops to fuse together, and when they do fuse together, as was shown in the lectures, the diagrams where the little loops were drawn, and you saw that uh, it forms one large magnetic loop which goes along this direction. As you can see, if these small loops all add up, then so these are the loops that will diffuse together. What will they form? They'll form one large loop along this direction, all along the surface of the sun. So what do we get? We get back a poloidal configuration, but now ulta. Okay. So this, we get back a poloidal configuration. So this the polarity of the magnetic field has flipped. It has switched. This is one solar cycle.
Actually, how is the solar cycle observed?
Okay, that's a very good question. You can, I think, detect the. So I think one does observe ionized particles, the motion of, let's say, charged particles, right? Because we have, let's say, probes for that. So then you would observe, you can detect the direction of the magnetic field, whether it's
I mean,
this or
uh, using which principle do they do it?
you would see the deflection on the charged particles, let's say, the motion of uh, charged particles. Plus, there's also these. They also observe behavior of sunspots, I think. So, in which phase you are in the solar cycle, the location of sunspots will, whether they're in the northern hemisphere or southern hemisphere. Of course, these things I don't know in details, and I'll have to cross check. Do not believe all of what I'm saying, or go cross check it. But I think activity of sunspots will also tell you whether you're in solar maxima, which is basically this, or solar minima, which is basically this. Or I might be wrong. Okay.
Okay.
Yeah. So, or which in which hemisphere?
That's what happens. I have been when I worked with someone who actually does this calculation. So that's when he taught that by detecting the solar spots and their motion throughout the day and calculating a number, the whole
Right.
number,
Right.
we can actually find out how it's
Great.
behaving.
Great. Yeah. 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 Okay. Okay. Yeah. Good. Good. Very good. Okay. All right. Uh, any questions from this? Okay, let me just check if I wanted to say anything else. Yeah, I think I've covered most of it. If no other questions are there, then I'll move on to discussing the sample assignment problems.
Yes, ma'am, I have one question.
Yeah, yeah.
In class, used this particular theorem called the Cowling-Satin dynamic theorem. So then there he uses axisymmetric velocity field.
Hmm.
I'm a bit unaware of that. Like, can you explain a bit what
Yeah,
exactly it means?
yeah. Sadly, even I am not, so I don't work with these things. But I think the theorem tells you that you can't. So axis symmetric just means something. The flow is symmetric about an axis. That's all it means, right? So all it all that theorem tells you is that if you have such a flow, so one might say that okay, to explain uh, these magnetic fields, I'll say that my fluid flow is along this direction because I know that my flux lines are frozen into the fluid. Then I can just say that, well, this is the symmetry of my flow, plasma flow. Hmm. And that can explain my toroidal field lines. I think the theorem tells you that this axisymmetric fluid flow does not give you this same magnetic field configuration with the same symmetry. Yeah, even I don't know the details of that, but yeah, I think that's all that tells you.
Actually, ma'am, I could not understand what exactly it means by the axisymmetric velocity field. Like the velocity,
Axisymmetric just means symmetric about some axis, right?
the velocity
So,
is not symmetric. Acha.
hmm, so let's say if you were considering, if I told you that so for example, if the fluid has the plasma in the sun has just velocity along this direction at every altitude, what is what symmetry, what is the axis of symmetry? This would be the axis of symmetry. This would be the axis of symmetry, right?
So velocity is moving along the symmetry axis of the symmetry. That's why it's when the field is generated accordingly.
It's not generated. That's what this theorem tells you, that you could say, you could attribute this toroidal configuration to a toroidal flow profile, right? The point is you can't do that.
Okay, ma'am. Now
I,
I
I
understand.
think I think I think that's what the theorem tells you.
Now I'm actually I was confused like run term. So now I understood.
Okay, okay, okay,
Thank
okay.
you, ma'am.
Good, good. Okay, all right. So shall I'll then move on to the sample assignment problems. Okay. Uh, all right. Ampere's law is given, and then it's told to you that popularly the current density in MHD is written as this. What does this imply? That the plasma velocities in MHD have to be non-relativistic, that there is no restriction of the plasma velocity, it can be whatever, however close to C.
I think it should be because there is something called relativistic MHD.
There is something called relativistic MHD, but this is not J for that.
And we cannot go arbitrarily close to C also. Won't it be A, ma'am? Because we have to think about non-relativistic particle.
We have absolutely. So in going from here to here, good, good, very good, very good. So in going from here to here, what we're doing is we're dropping this term. Now, if you look at the equation, that related E to B in the two frames, we swapped, remember, we swapped E for a V cross B. So there in this term, when we write it in terms of B, we get a V by C square. So to remind you, let me go back. So this was the equation. This was Ampere's law, right? So this is Ampere's law. What we did was we traded this del E del T for V cross B, del T of V cross B, and that gave us this equation. And there's a V by C over here, right? Which we dropped. Why? Because we're considering non-relativistic fluids. It is true that there's an entire uh, uh, hellhole of relativistic chemistry, and that's complicated stuff. But in our simplification, what we did was we assumed non-relativistic fluid that allowed us to drop this term and gave us this simplification. Hmm. So A is correct. Now among C and D, C tells you that current densities in MHD are always divergence free. That is, the divergence of the current density is always zero. D tells you current densities can have a finite divergence in MHD.
It should be C because
Absolutely.
divergence of curl is 0.
Absolutely, absolutely. So if you take this equation and take divergence on both sides, you'll see that divergence of J is 0. Very good. Very good. So the correct option is A and C. Alright. Uh, in ideal MHD, the electric field measured by an observer moving with the fluid is always negligibly small, versus in ideal MHD, the magnetic field measured by an observer moving with the fluid is always negligibly small. One option tells you that the electric field measured by an observer in the fluid frame is zero, negligibly small, and one tells you the magnetic field observed by such an observer is small.
A.
Hmm. Because
Absolutely. Very good, very good. A. Correct option is A. They always short it out, right? Because in ideal MHD, we're dealing with infinite conductivities. So the electric field is always small. Okay. Option C, in ideal MHD, the current density can have a source or sink. Option D, in ideal MHD, it can neither have a source nor a sink.
option
D.
B.
Absolutely. We just saw. Good. Very good. Correct option is A and D. All right. Uh, Consider a cubical volume element with B along Z direction, and B0 is a constant. Now we have to select the correct options. There will be no Lorentz force on the volume element. The volume element will experience some finite Lorentz force. It is not possible to say anything about the Lorentz force. The volume element will experience infinitely large Lorentz force.
No Lorentz force because there is no curl of B.
Absolutely, absolutely. So if you remember, the Lorentz force on a current carrying fluid element was J cross B, and J was rated to B as curl of B. So this is your Lorentz force. But what is B? B is B0, a constant times Z cap. So if you compute the curl of this quantity, it's going to be a 0. So there is no Lorentz force. So it's a force-free configuration. Okay. All right. So the correct option is A. All right. Choose the correct options. For a given boundary condition, a potential magnetic field configuration has the highest energy. To remind you, what is a potential magnetic field configuration? We knew that divergence of B is 0. This is one of the Maxwell's equations. Hmm? And uh, curl of B parallel to B is a force-free configuration. Why? Because Lorentz force is given by curl of B cross B. Hmm? So if curl of B is parallel to B, then this cross product becomes 0 and this becomes a force-free configuration. Then what we said was, if it's not parallel to B, but rather it's equals to 0, then what can we write? We can write B as some scalar of phi, it's a gradient of some scalar potential, scalar magnetic potential. Hmm? This curl of this gradient is always 0. And then we can use this over here to write Laplacian of phi is equals to 0. Divergence of gradient is Laplacian. So Laplacian of phi is always 0. So such a phi is called a potential magnetic potential, right? So for a given boundary condition, a potential magnetic field configuration has the highest energy. Such a configuration has the highest energy amongst all possible configurations that satisfy a given boundary conditions. Option B tells you that this has the lowest energy amongst all possible configurations. Which one will be true?
B.
B. Absolutely. Why? You can see, one can prove that if you have this B, then the energy, which is basically nothing but this B square, some constant times B square dV, energy contained in a certain volume because of this magnetic field. It goes as B square, right? Which is basically nothing but gradient of phi square dV. This quantity is a minimum if phi satisfies this equation. You can just take this equation. hmm, you can so this is the energy, right? This is the energy. What you can do is you can find the minima for this, which will be finding the solution for dE d phi equals 0. So you're looking for solutions phi that will satisfy dE d phi equals 0 given E is this, and you will see that you'll get an integrand. If you operate d d phi on this, you will get in the integrand you'll get Laplacian of phi. And if Laplacian of phi is 0, then dE d phi is 0, which means that it's a minimum energy configuration. Okay? So if phi satisfies this, the Laplacian of phi is 0, then the magnetic field corresponding to this configuration, this magnetic field, is the minimum energy configuration. So B is true. Alright, among C and D, for a given boundary condition, if the magnetic field is a non-potential configuration, it will tend to relax and finally attain a potential configuration. Versus, for a given boundary condition, the magnetic field is in a non-potential configuration. It will eventually relax to some other non-potential configuration.
C.
C. All systems tend to relax to minimum energy configuration, right? So C is true. So the correct option is B and C. Alright, so this concludes whatever I wanted to discuss today. If you have any questions, please ask. If not, I'll end the recording now.